All right, so now we're going to talk about differentials of a mapping. So let's consider a map. Okay, so let's say we have a map F. It's like from one manifold M to another manifold N, right? Okay, and then let's say we have a tangent vector. It's like C, which is at the tangent space. It's like at X. It's like of point X. It's like on M. Okay, then you can show that if you look at the differential of F, okay, at the point X, okay, in this direction, because C, then this acts on F in the following way. So this is a function. This is defined to be because C acting on F composed with big F. Okay, so let's try to draw a picture here. Okay, so you have manifold M and N. There's a map from M to N. It's like via big F. Okay, and then F obviously is a function. It's like on N. Okay, so we have a composition here, right, which again gives you a map F composed with little f composed with big F is a map then from M, it's like to the rails, okay? So this is just a scalar valid function. It's like on M, it's like, and you can apply, it's like the tangent vector, it's like 2M, it's like on this, right, as a essentially a directional derivative, right? And this basically induces, right, by this definition, an action of, you know, it's like some other tangent vector. It's like on the scalar value function. It's like on N, right? So, so the claim then is that this thing here, right, is a tangent vector on N. Okay, so this is an element of Tn. And in particular, you expect that this is based at a particular point, right? Which, you know, if you had to guess, it's like would be big F applied to the point X. Okay. Yeah. So, all right. So yeah. So again, the point is that if you were to formally look at the differential of the map, it's like at a particular point acting on a vector, right? Then this gives you a new vector. It's like to the manifold N, it's like at the point f of x. And since you define it's like tangent vectors by their action on scalar valued functions, it's like on that manifold, right? We want to act it on the manifold, and you can define it's like that action, it's like in this following way. Okay, right. So that's one way of thinking about it. Is like this is when you think of tangent vectors via their actions on sort of real value functions. It's like in the neighborhood. It's like of the point, right? As we sort of discussed before, you can also think about, you know, it's like representing a tangent vector in terms of, you know, curves which go through that point. It's like in some sense whose derivatives, it's like at that point all agree with each other. So so recall that we can sort of represent tangent vector by a curve gamma, right? So if for example it's like this cx, right? So if because Cx is is related, it's like to a representative curve gamma, and I'm going to put the square brackets around it to represent that the fact that I'm looking at the equivalence class of curves associated with that particular curve, right? Then the question is you know, what does d fx acting on c, which is what curve is this associated with, right? Okay, so so the way we see this is that gamma, right, is a map from the rails to m, gamma, right? And of course, we have a map from m to n, right, via this f. And so the natural curve to be looking at, right, is this composition, which is f composed with gamma, right? And indeed, as it turns out, it's like that's exactly what happens here, that the differential, it's like of the map, it's like applied to a vector, is represented by a curve, which is the composition of the representative curve, which represents c, with the f map. Okay, so this is f composed with c. Okay. So with that in mind, it's like then we can say something about this differential. So then the mapping df at x, right, can be viewed as a map from the tangent space at x to the manifold M. It's like 2 t fx n, okay, where you map, it's like a tangent vector to, it's like df x acting on c. Right, so this is a linear mapping. Which we call the differential. Or differential map. Derivative. Or tangent map. Of f at the point x. Okay. Right. And so if you recall, it's like, when we talked about immersions and submersions, it's like this was expressed, it's like in terms of properties of this differential map, right? So characterized in terms of it. So recall that f is an immersion, or sort of respectively a submersion, right? If and only if df of x, which is again a map from txm to t f of x n, right, is an injection, or if in the case of submersion, a surjection. So injection means that's one-to-one, and then a surjection means that's onto for every x on the manifold. Okay. All right. So the other thing you can do is to ask, well, what happens if n turns out to be a vector space? Okay. So if n is a vector space, say E, right, then the canonical identification between the tangent space at a point to the to the vector space, it's like with itself, right, yields the following, that df of x applied to a tangent vector is equal to, so I'm going to write this in terms of the basis for the vector space, all right, and that's equal to because Cx acting on the components, if you will, it's like of the map, right? So if so if f is a map from some manifold to a vector space, right, we can talk about the components, it's like of that map, right? F sub I, f super I, it's like, and then have that, and then that would be a scalar function, and then we have the vector field acting on that, and then that gives you a scalar, and then you can multiply it by the basis element. Okay. So, and you do this by the fact that where essentially f of x can be expanded as sum over I guess I should put I there, of fi ei. Let me just put fi of x just to be explicit, ei. Okay. Yes. So if n is actually just r, okay, then f is a real valued function. It's like on m, right? Then this reduces the following. We have that df of x acting on the vector is equal to cos cx of f, right? So, all right. So if you will, it's like, so this is a vector acting, it's like on a scalar valued function. And again, what happens is that what this suggests is that you can rewrite, it's like this action, it's like in terms of the differential, right? Okay, so, and again, you use the identification of the tangent space to a vector space with the vector space itself. So you're using the identification between the tangent space at x, it's like to the rails, it's like with the rails. Okay, so with that in mind, then we often denote a vector acting on a scalar function by this left-hand side, which is the linearization of the map acting on that vector. Okay, which emphasizes that this is a derivative. So this is just a question of notation, right? And again, it's like that notation is really just motivated by the observation that you have this equality here. It's like where the target space is actually just the rails. Okay, so let me just say one last thing about what happens if you happen to be on a linear manifold. It's like with sort of a linear space structure. So So if M and N are linear manifolds, right, then you can do the same identification, right? So more or less both have a vector space structure as well. So as was the case before, you can identify the tangent spaces with the manifolds themselves. You can identify TXM with M and TYN with N. And then, so with this, then this differential of the mapping reduces to the thing which you're familiar with. Okay, which is that df of x applied to some vector, right, is equal to the limit as t goes to 0 of f evaluated at x plus t times that vector, right, minus f at x divided by t. Okay, and then so given f, which is a map from M to N, and a vector field cos C on M, right, you let df acting on cos C denote the following mapping, right? So df of cos C is a map from the manifold now to Tn. Okay, so essentially what's happening, if you will, is that the differential to map maps tangent spaces to tangent spaces. Now you have a vector field, right? So maybe let's draw it over here, right? So you have M mapped to N, right? And this is the map from M to N. You have a vector field, okay, let's call that cos C, which is a map from M to Tm, again with the proviso that well, maybe let's just do this in the corner here. Okay, actually let me just sort of write it up here. Okay, so we have a map from M to N, which is F. We have a vector field, M to Tm, and if you recall, it's like there's this idea of a projection to M, and then this is the identity, okay? The identity mapping on M. So this is what is meant for this to be a vector field, is that maps M to Tm. It's like with the property that we can compose that map, then with the projection, you get the identity map here. Okay, so what you want to do is you want to think of the differential of this map F. It's like mapping vector fields to vector fields, right? So that's basically what's going to happen here, okay? And so this maps X, it's like to df at X of the vector field C evaluated at point X. Right. Okay, so there's a map Tn here, and then there's the differential df, right, which maps Tm to Tn. Okay, and so you can think of that as inducing something like sort of the push forward, it's like of the vector field, if you will. Okay. So, so in particular, given a real valued function f on M, right, and a vector field C on M, right, what we have is that df acting on this vector field is equal to just this vector field acting on F. Oh, sorry. Okay. All right. So the next thing we'll talk about are sort of tangent vectors. It's like to embedded manifolds and to quotient manifolds. And again, it's like the motivation for doing that is that we're trying to do optimization of manifolds, and the two important classes of manifolds which we're going to be working with, again, are embedded manifolds and quotient manifolds. So let me just stop here for now.